November 7th, 1943. Carpic Airfield, KH, France. The brutal headwinds over the English Channel had consumed fuel at an alarming rate. Second Lieutenant William E. Roach watched his fuel gauges spiral downward. The Pratt and Whitney R2800 sputtered, each cough a countdown to disaster. England lay ahead, tantalizing in its proximity, yet impossibly distant given what remained in his tanks. Beneath him, French farmland stretched in a patchwork quilt of occupied territory. Some fields friendly, most not. Then he spotted it, an airfield that could have been any Allied base he'd ever seen. Roach committed. The massive Republic P-47 Thunderbolt, serial 42 to 22490, call sign Beetle, kissed the grass smoothly. He followed a ground vehicle toward parking, killed the engine, and froze. The Balkenkreuz on nearby aircraft told him everything. Rifles surrounded his cockpit within seconds. The Germans he'd been hunting moments ago now had him. Lieutenant Roach's war as a fighter pilot had ended. He'd spend the duration behind barbed wire at Stalag Luftwaffe, but for the German Luftwaffe, an education was about to begin that neither side could have anticipated. What they found inside Beetle would shatter their understanding of American industrial might. The P-47 wasn't just a fighter, it was a complete philosophy made metal. American engineering, American production capacity, American abundance. Over 18 months, German engineers would strip it down, test it, fly it, and confront an uncomfortable reality. They hadn't simply fallen behind in some technological race. They'd been competing in an entirely different category of warfare. The captured Thunderbolts would teach lessons the Luftwaffe desperately needed but could never implement. Their nation lacked the resources, the infrastructure, the time. What American factories produced as standard equipment was, for Germany, an impossible dream. The capture wasn't the Luftwaffe's first encounter with the Thunderbolt. German pilots had been tangling with the beast since April 1943, when the 4th Fighter Group first shepherded B-17 seconds into hostile airspace. Initial combat reports dripped with contempt. Accustomed to nimble Focke-Wulf 190 seconds and Messerschmitt 109 seconds, they found the American fighter absurdly oversized, sluggish at low altitude, designed apparently by engineers who'd never studied aerial combat the German way. Throughout spring and summer, reports repeated the same criticisms: poor climb rate, ponderous handling below 15,000 feet, American pilots seemingly reluctant to dogfight. The consensus among veteran Luftwaffe pilots? The Thunderbolt was inferior, easily outmaneuvered where most combat happened. This assessment would prove catastrophically incomplete, yet buried in those same reports were troubling details that contradicted the narrative. Thunderbolts choosing to disengage couldn't be caught once they dove. 8 heavy machine guns delivered devastating firepower when Americans chose to engage. Armor seemed impervious to 7.92mm rounds, often shrugging off even 20mm cannon strikes. Most disturbing, badly damaged Thunderbolts kept flying. They limped home to England with wings shredded, engines streaming oil, control surfaces shot away still under pilot control, damage that would obliterate any German fighter. When Roach's intact Thunderbolt rolled to a stop at Carpic, the Luftwaffe finally had their chance for a proper examination. Local personnel immediately grasped the intelligence value. Within hours, armed guards surrounded Beetle. American markings vanished beneath German Balkenkreuz. Bright RLM, 4 yellow paint standard Luftwaffe, practice for captured aircraft splashed across undersurfaces and tail to prevent friendly fire from trigger-happy German anti-aircraft gunners. Shortly after, arrangements were made. Destination: Rechlin, the Luftwaffe's premier testing facility, roughly 100 kilometers northwest of Berlin in Mecklenburg. The aircraft received designation T9+FK, coding for the Circus Rosarius Evaluation Unit. Hans Werner Leer drew the assignment. Principal test pilot and chief engineer at Airprobungsstelle Rechlin, Leer would fly over 125 different aircraft types during the war, without a single crash or serious damage, a record bordering on miraculous. He approached the P-47 with professional curiosity tempered by caution. These systems were foreign territory. His first impression, later documented in his memoirs Luftwaffe Test Pilot, Flying Captured Allied Aircraft of World War II, was surprise at the cockpit's complexity. The instrument panel seemed to have twice the gauges of German fighters. Strange levers controlled systems he'd never encountered. The turbo-supercharger system demanded understanding of exhaust flow management principles that remained theoretical in German aviation but were apparently routine American practice. The constant-speed propeller operated differently from German equivalents. Most confusing, an elaborate automatic engine management system that German pilots handled manually through constant throttle and mixture adjustments. Leer wrote, "The P-47 cockpit could baffle even an experienced pilot. I gradually managed to ascertain the function of most of the levers and instruments, but there were also some obscure controls, the meaning of which was not immediately clear to me." He spent considerable ground time experimenting, studying the layout, a testament to his methodical approach when flying unfamiliar aircraft without manuals. The engine start sequence alone revealed sophistication beyond German standards. The Pratt and Whitney R2800 double Wasp required specific procedures to properly initialize its massive turbo-supercharger. Leer followed each step methodically, his engineer's mind cataloguing purposes. When the 18-cylinder radial roared to life, it produced a sound utterly unlike the sharp bark of German inline engines or even the BMW 801 radial in the FW 190. This was a deep, powerful rumble, enormous displacement, and tremendous reserves held in check. Taxiing, Leer felt the weight through every control input. The P-47D weighed nearly 10,000 pounds empty. This example still carried substantial fuel and full ammunition closer to 13,500 pounds. By comparison, the FW 190 Amperes 8, among Germany's heaviest single-seaters, weighed 7,650 pounds empty, roughly 10,800 at maximum load. The Thunderbolt was genuinely massive for a single-seat fighter, larger than some Luftwaffe twins. Leer advanced the throttle for takeoff. The difference between German and American engineering philosophy became immediately apparent. The R2800 developed 2,000 horsepower at standard boost, reaching 2,300 with water methanol injection. Germany's BMW 801D finest radial in production, powering the FW 190 managed between 1,700 and 1,730 horsepower at maximum continuous settings. Even with this power advantage, the P-47's greater weight meant a longer takeoff run than Leer expected, consuming nearly the entire grass field. But once airborne, he began discovering why German pilots who'd only fought Thunderbolts at low altitude had fundamentally misunderstood the machine. He climbed steadily, nursing the turbo-supercharger to operating temperature. Below 15,000 feet, the P-47 felt exactly as combat pilots described: heavy, sluggish in turns, unable to match German fighters in maneuverability. Climb rate was mediocre at best compared to the FW 190 or BF 109. In this regime, any competent German pilot in a contemporary fighter could outmaneuver the Thunderbolt in sustained turning combat. But somewhere above 20,000 feet, the aircraft transformed completely. The turbo-supercharger, driven by exhaust gases, increasingly efficient as air pressure decreased, began forcing massive quantities of compressed air into the cylinders. While German engines gasped for oxygen and bled power, the R2800 maintained full rated output. At 25,000 feet, where German fighters operated at perhaps 70% of sea-level power, the Thunderbolt's engine still produced full rated output. Leer pushed the throttle forward at 25,000 feet. The Thunderbolt accelerated with surprising vigor for such a large aircraft. He rolled into a dive to test high-speed characteristics. The aircraft responded with enthusiasm bordering on violence. The P-47 blew past 500 miles per hour in a steep dive, reaching speeds where controls stiffened dramatically as airflow compressed around the airframe. Recovery required both hands on the stick and considerable physical strength. The aircraft was approaching compressibility limits that wouldn't be fully understood until the jet age. The roll rate impressed Leer immediately, contradicting everything German pilots assumed about the heavy American fighter. Despite size and weight, the Thunderbolt rolled faster than any German fighter Leer had flown, including the FW-190, considered excellent in roll performance. Combined with devastating dive speed, this created a tactical advantage German pilots had been reporting without fully grasping implications. An American pilot in trouble at high altitude could simply roll inverted and dive away at speeds no German fighter could match. Any Luftwaffe pilot attempting pursuit would encounter compressibility effects. The P-47's stronger airframe and more effective controls handled more successfully. Leer flew the captured Thunderbolt through a comprehensive test program, exploring the flight envelope systematically per standard Rechlin procedures. His preliminary report contained observations that troubled Luftwaffe headquarters staff, still believing German designs were fundamentally superior. At altitudes above 25,000 feet, where aerial combat increasingly occurred as Allied bombers flew higher to escape flak, the P-47 wasn't inferior to German fighters. It was superior in specific crucial ways that negated German advantages in maneuverability and climb rate. Over following weeks, Rechlin's engineers subjected Beetle to exhaustive testing. They photographed every component from multiple angles, measured every dimension with precision instruments, weighed every major part and assembly, tested every system under various conditions. The turbo-supercharger received special attention. This technology represented the primary difference between American and German approaches to high-altitude performance. What detailed examination revealed shocked engineers accustomed to resource-constrained design philosophy. The Pratt and Whitney R2800 double wasp, 18 cylinders arranged in 2 rows of 9 around a central crankshaft. Total displacement, 2,840 cubic inches, equivalent to 45.9 litres. The BMW 801D displaced 2,560 cubic inches, 41.8 litres. But displacement alone didn't explain the significant power difference. The R2800 incorporated forged aluminum alloy pistons, sodium-cooled exhaust valves for extreme temperatures, and a crankshaft forged from high-grade steel alloy that German metallurgists examined with professional envy, recognizing materials they could no longer obtain in sufficient quantities. American materials quality and manufacturing precision astounded the inspection team. Every component showed precision manufacturing to tight tolerances. Surface finishes were consistently smooth. The magnetos used increasingly scarce materials. Spark plugs incorporated superior ceramics. The fuel injection system operated with precision. German engineers associated with laboratory equipment, not combat aircraft expected to function reliably under harsh conditions. Most tellingly, the entire engine showed no signs of material substitution or quality compromises, forced by resource limitations. The Americans had built this exactly as designed, using all specified materials without the desperate improvisations, increasingly characterizing late-war German production. The turbo-supercharger system revealed engineering sophistication Germany had attempted but never successfully implemented in production aircraft. Exhaust gases from all 18 cylinders were collected through manifolds, routed through insulated pipes along each fuselage side to a turbine unit behind and below the cockpit. This turbine, spinning at tremendous speed driven by hot exhaust, drove a centrifugal compressor, forcing additional air into the engine's supercharger. The system included an intercooler to reduce compressed air temperature, increasing density and preventing destructive detonation. Automatic regulators controlled boost pressure and turbine speed without constant pilot intervention beyond setting desired manifold pressure. German engineers understood the theoretical principles perfectly. They'd conducted experimental programs exploring similar approaches, but implementing such systems in mass-produced combat aircraft had proven impossible given material shortages and manufacturing limitations plaguing German industry by 1943. The turbo-supercharger required exotic high-temperature alloys for turbine blades, withstanding extreme temperatures while spinning at high speeds. The control system demanded precision manufacturing and reliable components. Extensive ducting needed heat-resistant materials and perfect seals. Every element had to work reliably in combat exposed to vibration, temperature extremes from -60 Fahrenheit at altitude to over 200 near the engine, and potential battle damage. The Americans had solved all these problems and installed the complete system as standard equipment on every P-47 produced. Not experimental equipment for special missions or limited runs, simply how the airplane worked, installed in thousands of examples. This casual implementation of advanced technology as standard production equipment revealed industrial capacity German engineers found difficult to fully comprehend. German technical reports from Rechlin noted that the turbo-supercharger system alone represented engineering sophistication and manufacturing capability exceeding current German capacity to replicate in production quantities. The materials, precision manufacturing, and quality control required to produce such systems reliably at scale simply exceeded what German industry could achieve in 1943, given strategic material shortages and progressive manufacturing standards, degradation from Allied bombing and replacement of skilled workers with forced labor. The armament installation provided another lesson in American abundance. The P-47D mounted 8 Browning M2, 50 caliber machine guns, 4 per wing. Most German fighters carried mixed armament, typically 4 machine guns and 2 20mm cannons, or in early models, 6 machine guns total. The American decision to install 8 heavy machine guns represented deliberate choice to maximize firepower despite additional weight and complexity. Each gun fed from a separate ammunition box built into wing structure, 425 rounds per box. Total ammunition capacity, 3,400 rounds across all 8 guns. The FW 190 amperes typically carried approximately 2,000 rounds total for machine guns and 500 for cannons. The P-47 pilot could fire all 8 guns continuously for approximately 20 seconds before exhausting ammunition, combined rate of fire approaching 100 rounds per second. When all 8 guns were properly harmonized to converge at a single point, the volume of fire was simply overwhelming. German test firings documented the devastating effect. Installation quality impressed armament specialists. Each gun mounted in an electrically heated bay, preventing freezing at high altitude, where temperatures could drop to -60 or lower. Spent cartridge cases and disintegrating belt links were collected through chutes, ejected through ports in the wing's lower surface, preventing damage to aircraft or interference with control surfaces. The system functioned flawlessly during testing. Despite firing thousands of rounds under varying atmospheric conditions, no jamming or feeding malfunctions recorded. Ammunition quality revealed another dimension of American industrial capability. The 50 caliber rounds used armor-piercing cores manufactured to consistent specifications, incendiary compounds functioning reliably, tracer elements burning predictably. Testing revealed American ammunition was consistently more reliable than equivalent German production, which had suffered quality degradation as strategic materials became scarce. The Thunderbolt's armor protection demonstrated American willingness to accept significant weight penalties for pilot survivability, a philosophical difference from German design priorities. The cockpit was surrounded by heavy armor plate on multiple sides. The pilot sat in what American designers called an armored bathtub, providing protection from below and behind. The windscreen incorporated thick, bulletproof glass-stopping machine gun rounds and resisting cannon shell fragments. Additional armor plates protected critical systems, including oil coolers and the vulnerable turbo-supercharger. Total armor weight exceeded 200 pounds, roughly equivalent to adding 2 additional machine guns with ammunition. German fighters typically carried less comprehensive armor protection, prioritizing lighter weight and better performance, while accepting higher pilot casualties as an unavoidable cost. The design philosophy difference revealed itself in maintenance accessibility. American designers clearly anticipated mechanics working in forward air bases would need to service aircraft quickly, possibly at night, possibly in adverse weather, possibly under threat of enemy attack. Every major component could be accessed through large panels secured with quick-release fasteners requiring only simple tools. The massive engine could be changed in the field within hours, using standard hoisting equipment and clearly documented procedures. German fighters, designed expecting factory-level maintenance for major repairs, typically required more extensive disassembly for major component service. This difference reflected American abundance versus German scarcity. The Americans could afford dedicating engineering resources to maintainability because industrial capacity allowed optimizing designs for operational efficiency rather than pure production efficiency. The radio installation represented another area where American technology exceeded German equivalents. The aircraft carried an SCR 274 newtons command radio for air-to-air and air-to-ground communication, plus an SCR 515 amperes liaison radio providing additional channels. Both units operated with clarity and range, exceeding contemporary German capabilities. German radio systems suffered persistent interference problems. American engineers had apparently solved through superior component design and better shielding. The radios also integrated with an identification friend or foe system, automatically identifying friendly aircraft to ground controllers, preventing friendly fire incidents. This automated identification sophistication was something German forces lacked in 1943. Perhaps the most profound revelation came not from any single advanced system, but from the cumulative impression of quality and completeness throughout the aircraft. Every component appeared to be the best possible version American engineers could design and manufacturers could produce. Nothing was obviously compromised due to material shortages. Nothing showed clear evidence of substitute materials because preferred materials were unavailable. Nothing reflected the desperate improvisations, increasingly characterizing German late-war production as strategic bombing. Degraded industrial capacity and material shortages became acute. German technical reports compiled at Rechlin and distributed through Luftwaffe technical services emphasized this point repeatedly. The P-47 had been built exactly as designers intended, using all specified materials and processes with no apparent compromises forced by resource scarcity. This level of manufacturing fidelity to original design specifications was becoming increasingly difficult for German industry as the war progressed. Flight testing continued through winter 1943 into early 1944, as additional P-47 seconds were captured and brought to Rechlin for comparative evaluation. On May 29, 1944, another P-47 landed in German hands when Second Lieutenant Lloyd S. Hathcock of the 301st Fighter Squadron, 332nd Fighter Group, became disoriented during a ferry flight and mistakenly landed at enemy-held Rome Littorio airfield in Italy. His aircraft, serial 42-75971, was quickly seized. This P-47 had previously been the personal mount of George Noetzel, an 8-victory ace with the 317th Fighter Squadron. The Germans transferred the aircraft to Verneuchen, where it was initially designated 8+6, then later transferred to Circus Rosarius on October 12, 1944, receiving designation T9+LK. Testing data accumulated at Rechlin produced tactical recommendations compiled and distributed to frontline Luftwaffe fighter units. These recommendations advised engaging P-47 seconds below 15,000 feet offered the best probability of success, as the Thunderbolts' poor low-altitude performance and slow climb gave German fighters clear advantages in that regime. Pilots were specifically warned against diving away from attacking Thunderbolts. The American fighter would simply accelerate to unmatchable speeds. Reports emphasized damaged P-47 seconds, frequently continued flying despite battle damage that would destroy German fighters, so attacks needed to be pressed home aggressively with concentrated fire, rather than assuming a few hits would down the aircraft. But tactical advice, however useful to individual pilots, couldn't address the fundamental strategic problem, becoming increasingly apparent. Germany was fighting an opponent with effectively unlimited material resources relative to German industrial capacity. Every damaged or destroyed P-47 was replaced within days, from production exceeding 300 aircraft monthly at peak output. American pilot training programs produced skilled aviators in quantities Germany could no longer match, as training was compressed and fuel shortages limited flight hours. The logistics system supporting American Thunderbolt operations delivered fuel, ammunition, and spare parts without apparent constraint, while German logistics deteriorated under relentless Allied air attack. The captured P-47 seconds were eventually transferred to Circus Rosarius, the special Luftwaffe demonstration unit commanded by Flugkapitän Theodor Rosarius. This specialized unit traveled to frontline fighter bases throughout occupied Europe, allowing German pilots to see captured Allied aircraft firsthand and learn recognition features and combat characteristics. The demonstrations served dual purposes, educational and psychological. Pilots learned visual recognition features and tactical characteristics of enemy aircraft they'd face in combat. But they also saw physical evidence that Allied equipment was often superior in specific important capabilities, particularly at high altitudes where combat increasingly occurred. Post-war interviews with Luftwaffe pilots who attended these demonstrations revealed the psychological impact of seeing captured American fighters' capabilities demonstrated directly. While Circus Rosarius pilots could show German fighters maintained advantages in certain flight regimes, particularly medium altitudes, the demonstrations made clear that at altitudes where American bomber formations operated, escorted by P-47 seconds and later P-51 seconds, German fighters were at a distinct disadvantage. Intelligence gathered from captured P-47 seconds included detailed performance data directly contradicting optimistic assumptions that had circulated in earlier Luftwaffe briefings. At sea level, the P-47D achieved approximately 350 miles per hour, not particularly impressive compared to the FW, 190 amperes 408 miles per hour at the same altitude. At 10,000 feet, the Thunderbolt reached approximately 375 miles per hour, but at 30,000 feet, the P-47 achieved 426 miles per hour, while the Focke-Wulf struggled to reach 370 miles per hour, and the Bf-109G managed approximately 385 miles per hour. The performance advantage at combat altitudes was clear, decisive, and growing more important as Allied bomber formations flew higher to escape German anti-aircraft fire. Service ceiling comparisons proved equally discouraging. The P-47 Thunderbolt's service ceiling reached 42,000 feet. German fighters rarely operated effectively above 35,000 feet, performance degrading rapidly at higher altitudes due to reduced engine power in thin air. American bomber formations could and did operate at altitudes where German interceptors could barely reach them, and where interceptors that did reach combat altitude had insufficient power reserves for effective maneuvering. P-47 escorts operated comfortably at these altitudes, maintaining full combat capability while German fighters struggled. Range comparisons revealed another dimension of American industrial and logistical superiority. With external fuel tanks, the P-47D could escort bombers on missions penetrating deep into Germany. Early P-47 models had limited range restricting effectiveness, but by 1944, Thunderbolts equipped with drop tanks routinely flew missions covering 1,000 miles or more. German fighters, designed primarily for short-range interception missions defending the Reich, lacked internal fuel capacity for extended operations. The difference in operational radius meant American fighters could engage at times and places of their choosing, while German fighters were forced to fight defensively. Captured Thunderbolts also provided insights into American pilot training and tactical doctrine through examination of gun camera footage and analysis of combat damage patterns on aircraft that survived combat before capture. Evidence suggested American pilots consistently employed tactics emphasizing the P-47's strengths while avoiding situations exposing weaknesses. They maintained high altitude where the turbo-supercharger provided clear advantage. They used dive and zoom attacks rather than attempting sustained turning dogfights where German fighters held advantage. They worked in coordinated pairs or four-ship flights rather than engaging individually, maintaining mutual support even when this meant declining apparently advantageous individual engagement opportunities. The discipline evident in American tactical execution impressed Luftwaffe analysts studying the evidence. Many Luftwaffe pilots, particularly experienced aces, preferred fighting individually relying on personal skill and aggressive tactics to achieve victory. American pilots appeared to follow established doctrine consistently, supporting each other systematically, rarely allowing individual pride or aggression to override tactical sense. This disciplined approach, combined with superior high-altitude equipment and growing numerical advantage, created a combination even veteran German pilots found increasingly difficult to overcome as the war progressed. By D-Day in June 1944, the strategic situation had deteriorated to where intelligence on captured aircraft provided little practical value to Germany's war effort. The Luftwaffe understood clearly that American equipment was superior in important ways. They comprehended American tactics. They had detailed technical data on Allied aircraft performance, but this knowledge couldn't produce the resources, strategic materials, manufacturing capacity, and trained personnel needed to compete effectively. Rechlin reports, carefully compiled and professionally distributed throughout Luftwaffe technical services, served primarily to document the technological and industrial gap driving Germany toward inevitable defeat. The comparison between American and German engine production illustrated the impossible position Germany faced. Pratt and Whitney, along with Ford Motor Company, produced over 125,000 R2, 1,800 engines by war's end. Production of this single engine type exceeded Germany's entire combat aircraft engine production. BMW produced approximately 61,000 examples of the 801 radial throughout the entire war. The Daimler-Benz DB605, Germany's most produced inline engine, reached approximately 42,400 units total. American production of one advanced engine type surpassed Germany's total output of all combat aircraft engines combined. American industry in 1944 produced approximately 96,000 aircraft, while Germany reached approximately 25,000 of all types. The United States produced 38,000 fighters alone, plus 16,000 heavy bombers, plus thousands of medium bombers, transports, and trainers. Combined with British and Soviet production, the Allied advantage exceeded 5-1 by 1944. The industrial base supporting this production operated on a scale Germany couldn't match. The Aluminum Company of America alone produced more aluminum than Germany's entire aluminum industry. Individual American steel plants frequently outproduced the entire Ruhr industrial region. Automotive factories, manufacturing vehicles, operated on moving assembly lines while German plants used batch production methods. Even the machine tools that built the machines that built the aircraft were themselves produced in quantities, allowing American industry to supply not only its own requirements, but also substantial quantities to British and Soviet allies. The captured P-47 seconds ultimately ended their service in the chaotic final months of the European War. The aircraft designated T-9 plus FK, originally William Roach's Beetle, was recovered by American forces at Göttingen in May 1945, found among a collection of captured Allied aircraft the Germans had been evaluating. Photographs taken by American forces show the aircraft still wearing partial German markings, parked alongside FW-190 seconds and BF-109 seconds in what was effectively a museum of captured equipment, documenting the breadth of the Luftwaffe's intelligence-gathering effort. The Thunderbolts that served with German evaluation units provided German pilots and engineers with an education they desperately needed, but received too late to matter strategically. The aircraft demonstrated that American industrial philosophy prioritized absolute capability over elegant efficiency, abundant resources over careful optimization, systematic material advantage over individual technical excellence. These priorities, implemented with nearly unlimited resources and manufacturing capacity, produced weapons systems outclassing German equivalents in aggregate, even when German designs showed superior characteristics in specific isolated parameters. The lesson extended far beyond the P-47 itself. Every category of captured American equipment told the same fundamental story. The B-17 Flying Fortress, with its quartet of turbo-supercharged Wright Cyclone engines, represented strategic bombing capability Germany never achieved. The P-51 Mustang, combining American airframe engineering with the British Rolls-Royce Merlin engine, created what many historians consider the finest piston engine fighter of the entire war. The P-38 Lightning, with its twin turbo-supercharged engines and tricycle landing gear, demonstrated American willingness to pursue unconventional solutions. Each aircraft type revealed the same fundamental American approach: solve problems through superior engineering supported by unlimited industrial capacity rather than through clever optimization constrained by resource scarcity. Luftwaffe analysts clearly observed they weren't being defeated by superior tactics or better trained pilots, though American training programs were producing adequate pilots in overwhelming numbers. They were being defeated by an industrial system that could design adequate equipment and produce it in quantities, rendering German qualitative advantages increasingly irrelevant. Americans designed to their industrial strengths, leveraging massive manufacturing capacity, abundant raw materials, and efficient logistics. Germany, by 1943, was designing despite crippling industrial limitations, attempting to achieve through engineering cleverness what they could no longer accomplish through industrial might. The strategic implications were well documented throughout the Luftwaffe's technical services. By end of 1943, Germany had entered the war with arguably the world's most advanced air force, equipped with aircraft generally superior to opponents on a one-to-one basis. German pilots were better trained initially. German tactics were more refined. But German industry fundamentally lacked capacity to sustain these advantages when facing opponents with vastly greater industrial resources. American aircraft production doubled repeatedly: 1,940, 1,941, 1,942, continuing expansion until by 1944, American factories were producing over 96,000 aircraft annually, while Germany never exceeded 40,000 inches any year, despite desperate efforts. The quality gap between American and German aircraft widened steadily rather than narrowing. In 1942, German aircraft were often superior. By 1944, American aircraft equaled or exceeded German designs in virtually every important category. By 1945, the gap had become a chasm. American fighters, like the P-51 Hours and P-47 Newtons, represented evolutionary refinement of already excellent basic designs. German fighters, like the Ta-152, represented desperate attempts to extract more performance from industrial systems, collapsing under combined weight of strategic bombing, raw material shortages, and replacement of skilled workers, with poorly trained forced labor. The psychological impact on Luftwaffe morale of facing endless streams of capable enemy aircraft proved as destructive as material losses. German pilots reported feeling less like warriors in honorable combat and more like targets in a systematic destruction campaign. No matter how many Allied aircraft they shot down, more appeared the next day. No matter how skillfully they fought, American numerical superiority eventually prevailed through sheer attrition. The knowledge that their opponent's equipment was often superior, delivered in far greater quantities, supported by better logistics, and flown by adequately trained pilots quickly replaced when lost, created a pervasive sense of inevitable defeat, spreading throughout fighter forces during 1944. The captured P-47 seconds served as tangible physical evidence of this reality. Not propaganda claims or exaggerated intelligence reports. Actual aircraft German pilots could examine directly. The Thunderbolt wasn't some miracle weapon or revolutionary technological breakthrough. It was simply a very good fighter aircraft properly designed for its mission, adequately powered, well armed, appropriately protected, and manufactured in quantities sufficient to overwhelm opposition through systematic application of material superiority. The final historical irony: the Germans learned these lessons thoroughly, documented them professionally, grasped the implications completely, yet could never apply the knowledge gained. Understanding American industrial superiority didn't grant Germany the aluminum, steel, fuel, skilled labor, undamaged factories, and functioning transportation networks needed to produce equivalent aircraft in equivalent quantities. Knowing the P-47's exact capabilities didn't provide the high-temperature alloys, precision manufacturing equipment, quality control systems, and trained workforce needed to build comparable turbo-supercharger systems. Intelligence gathered from captured aircraft documented the dimensions of German defeat with professional thoroughness, without offering any realistic path to avoid that defeat. When Allied forces captured Rechlin and associated facilities in May 1945, they found extensive documentation of the captured aircraft evaluation program. German technical reports filled filing cabinets, detailing every measurable characteristic of every American and British aircraft examined during the war. The reports were models of technical thoroughness and scientific objectivity. They also represented thousands of man-hours spent meticulously documenting capabilities Germany could observe and measure, but never replicate, given their deteriorating industrial situation. American technical intelligence teams reviewing German reports after the war noted with professional interest that German engineers had understood American aircraft capabilities more clearly and in greater detail than American commanders sometimes did. The Germans had identified weaknesses in American designs that American pilots learned to work around through experience. Technical analysis was frequently more detailed and rigorous than equivalent American evaluations of their own equipment. German engineering competence had never been in question, but American reviewers also noted what the German reports implicitly revealed about Germany's strategic situation. Germany had attempted to fight a modern industrial war with an industrial base insufficient for the task. They'd compensated through excellent engineering, superior pilot training in early war years, and tactical innovation born of necessity. These advantages sustained them through early victories, against opponents with similar resource constraints. But against an opponent like the United States possessing industrial capacity exceeding all other major powers, combined excellent engineering and tactical skill could only delay the inevitable outcome rather than change it. The story of German engineers examining captured P-47 Thunderbolts provides a clear case study in the realities of industrial warfare as it had evolved by the Second World War. The Thunderbolt succeeded not because it was the absolute best possible fighter by every conceivable measure, but because it was a very effective fighter produced in quantities making isolated examples of technical superiority strategically irrelevant. American industry built 15,683 Thunderbolts while simultaneously building 15,486 P-51 Mustangs, 10,037 P-38 Lightnings, 13,738 F-6F Hellcats, and 12,571 F-4U Corsairs. Total American fighter production exceeded 70,000 aircraft during the war. Each aircraft represented thousands of hours of skilled labor, tons of aluminum and steel, hundreds of precision components, and manufacturing capacity Germany couldn't approach. The P-47 Thunderbolt became a symbol of American industrial dominance to German pilots who fought it. Luftwaffe pilots used the same nickname American pilots coined, calling it the Jug, in acknowledgement of its ungainly appearance. They also called it Indiana, after the Thunderbird emblem many squadrons painted on engine cowlings. As losses mounted and the strategic situation deteriorated, some referred to it simply as that 8-gun fighter, and learned through bitter experience to avoid engaging Thunderbolts at altitudes where the American fighter held tactical advantage, which increasingly meant avoiding combat above 20,000 feet, where the turbo-supercharger gave the P-47 decisive performance superiority. By war's end, P-47 Thunderbolts had destroyed approximately 3,752 enemy aircraft in aerial combat, while approximately 3,499 P-47 seconds were lost to all causes, including operational accidents, mechanical failures, and ground attack missions. This roughly 1-to-1 exchange rate in total losses appears unremarkable until one considers the Thunderbolt served primarily in ground attack from mid-1944 onward, facing intense anti-aircraft fire during low-level missions rather than engaging primarily in air-to-air combat. In the pure fighter escort role during 1943 and early 1944, P-47 seconds achieved significantly better exchange rates, particularly at high altitudes where the turbo-supercharger advantage was most pronounced. The ground attack role revealed yet another dimension of American design philosophy, emphasizing versatility. When P-51 Mustangs with superior range began taking over bomber escort duties in 1944, the 9th Air Force reassigned many Thunderbolt groups to tactical air support missions. The rugged P-47, with its reliable air-cooled radial and heavy armor, proved exceptionally well suited for dangerous low-altitude attack missions. The same characteristics making it seem ponderous in low-altitude dogfights: substantial size, heavy weight, comprehensive armor, powerful armament made it nearly ideal for ground attack, where survivability and firepower mattered more than maneuverability. Thunderbolt pilots flying ground attack destroyed staggering quantities of German military equipment. Official claims documented through gun camera footage and after-action reports included over 86,000 railway cars, 9,000 locomotives, 6,000 armored fighting vehicles, and 68,000 trucks destroyed or damaged. While such claims inevitably included some duplication, the scale of destruction was undeniable and had measurable impact on German military operations. The P-47, armed with bombs and rockets in addition to its 8 machine guns, had evolved into a true multi-role combat aircraft. German ground forces learned to recognize and fear the characteristic sound of Pratt and Whitney R-2000 800 radial engines at low altitude. The deep rumble provided warning of impending attacks German troops were largely helpless to prevent. The psychological impact of constant air attack, combined with substantial material losses and disruption of logistics and communications, measurably degraded German ground forces' combat effectiveness. Throughout 1944 and 1945. The question of what happened to specific captured aircraft provides an epilogue. William Roach's P-47D Beetle, serial 42-22490, designated T-9+FK by the Germans, survived the war and was recovered by American forces at Göttingen in May 1945. After evaluation by American intelligence teams examining German testing procedures, the aircraft was eventually scrapped. Lloyd Hathcock's P-47D, serial 42-75971, designated T-9+LK, met a similar fate, recovered but not preserved for historical purposes. The pilots' fates after capture differed markedly. William Roach spent the remainder of the war at Stalag Luft I in Bath, Germany. He was liberated by Soviet forces in May 1945 and returned to the United States. Lloyd Hathcock spent 11 months as a prisoner of war, primarily at Stalag Luft III site of the famous Great Escape that had occurred just 3 months before his arrival. He was the only African-American pilot among thousands of white prisoners at the camp. When Soviet forces advanced westward in January 1945, German forces evacuated the camp, forcing prisoners on a brutal winter march to Stalag 7 Amperes, then Stalag 13D. He was liberated by Allied forces in April 1945. Hathcock returned to the United States and played a significant role in post-war desegregation of the U.S. Air Force. He later pioneered innovations in aerial reconnaissance photography at Wright-Patterson Air Force Base. Hans Werner Leer survived the war despite flying 125 different aircraft types, including numerous captured Allied aircraft throughout the conflict. His remarkable safety record, never crashing or seriously damaging a single aircraft throughout his test pilot career, stands unique in aviation history. After the war, he provided extensive debriefings to Allied intelligence services about German aircraft development programs. His memoirs, published in 1,977 inches German and translated into English in 1980, provide one of the most detailed first-hand accounts of the German captured aircraft evaluation program and offer valuable insights into how the Luftwaffe assessed Allied aviation technology. The broader lesson emerging from the story of captured P-47 Thunderbolts in German hands transcends the specific technical details of one aircraft type. The Thunderbolt evaluation at Rechlin demonstrated that by 1943, the outcome of the air war over Europe was being determined not by pilot skill, tactical innovation, or even aircraft performance in narrow technical terms, but by industrial capacity applied at a national scale. The nation that could design adequate equipment and produce it in overwhelming quantities, while simultaneously producing everything else a modern military requires, would inevitably defeat opponents who produced technically superior equipment in insufficient quantities. Germany's situation by late 1943 was that of a nation attempting to compete industrially against opponents whose combined industrial capacity exceeded German capacity by factors of 5 or more. When Britain refused to capitulate after France fell, when the Soviet Union survived the initial German onslaught and relocated its industry beyond German reach, and when the United States entered the war with its vast, untouched industrial base, Germany's path to military victory effectively closed. The only question was how long Germany could continue fighting and how much destruction would occur before the inevitable conclusion. The story of Beetle and the other captured Thunderbolts at Rechlin thus becomes a microcosm of Germany's broader strategic dilemma. German engineers could examine American equipment, understand American capabilities, and accurately assess American industrial strength. This knowledge was professionally gathered, carefully analyzed, and thoroughly documented. But knowledge alone couldn't produce the aluminum, steel, rubber, fuel, machine tools, skilled workers, undamaged factories, and functioning railroads required to compete with American industrial output. The Republic P-47 Thunderbolt, examined in minute detail by German engineers at Rechlin, proved a final truth about industrialized warfare in the 20th century. Material abundance systematically applied through competent engineering and adequate tactical execution would defeat technical excellence constrained by resource scarcity. The most powerful element in America's arsenal wasn't any individual technology, however impressive, but rather the complete industrial system that could conceive, design, develop, test, produce, and logistically support thousands of complex weapons systems simultaneously, while maintaining quality and continuously improving designs based on combat experience. The captured Thunderbolts taught this lesson with undeniable clarity. German engineers measured it precisely, documented it professionally, and reported it accurately through their chain of command. The lesson arrived too late to matter. By the time William Roach's Beetle was being meticulously examined at Rechlin in late 1943, the outcome of the war was already determined by industrial mathematics that no amount of German engineering skill or pilot courage could overcome. The Thunderbolts, sitting on German airfields, wearing hasty Balkenkreuz markings over American stars, represented a future that had already arrived, one in which industrial capacity had become the decisive factor in modern warfare,